last class we discussed about wideband amplifiers which used pairs without any feedback, and we came out with a very important configuration, that is cascode configuration for the wideband. And we had other configurations like common collector cascaded to common base, common collector cascaded to common emitter, things like that. So, in this series of lectures we will discuss about negative feedback and its use in widebanding. So, ultimately we will go to negative feedback wideband integrated circuits, amplifiers. So, let us now just revise our knowledge about negative feedback. We had seen earlier that negative feedback we have to give cautiously. In case negative feedback is likely to turn itself into a positive feedback and result in oscillation, that is a dangerous thing, because we have to cut down the oscillations by introducing dominant pole, and that will cut down the bandwidth further. So, if at all we use negative feedback, the negative feedback amplifier should not need any frequency compensation. That is the condition of negative feedback that we must utilize in widebanding. We have seen that any negative feedback system which has 3 or more dominant time constants will invariably result in serious problem about oscillations. Only systems which are less than third order, that means only first order and second order systems will not oscillate when used under negative feedback. Okay. So, the best system therefore is the one that is simplest, first order system. But we know that a single stage amplifier, for example a common emitter amplifier, has 2 time constants, input time constant and output time constant. So, the minimum order of a single stage itself is going to be 2. So, if we cascade more number of stages, we are landing ourselves in more problems, because the order of the system will increase above 2, it will become 3 or more. Further, the loop gain is also going to increase. The consequent need for a frequency compensation become more serious there. Therefore, the best negative feedback configuration for widebanding is a single stage. Now, how do we have the negative feedback arrangement for a single stage? Let us consider. If it is a single stage transistor, we know that only 2 types of negative feedback will be valid. What are those? Out of H, Y, Z, G type of feedback, what are those which are possible in a single stage which will result in negative feedback? Y and Z type of feedback. So, we know that only Y feedback and Z feedback are the allowed types of feedback if it is to become negative. What is the purpose of this type of feedback? Let us say Y feedback. Input admittance and output admittance, okay, what happened to them? Right? Input admittance is increased, right? That means input admittance is made to go towards as high a value as possible. Right? Output admittance is going to be increased, right? That means it is leading you towards idealization of what kind of amplifier? Current control. Current control voltage source. So, this is going to lead you towards current controlled voltage source. The dual of that is voltage controlled current source, that is nothing but Z feedback. Voltage controlled current source is the dual of that. That means, if I put Z feedback, input impedance is going to increase, output impedance also is going to increase, and therefore, it is going towards an idealization towards voltage controlled current source. Now, this is important. What is idealization? That means, the forward transfer parameter corresponding to that type of source is going to become desensitized with respect to active parameter. Let us see what this forward transfer parameter is. If it is Y feedback, the type of feedback structure is going to be this. This is Y feedback. How about Z feedback? You will have the same configuration like this, but it will come in series at the input and series at the output. So, we have here this nothing but this is the feedback element, which is nothing but Z feedback. We will call this RF, capital F. So, what will be the transfer parameter that is going to be desensitized in this particular case? Forward transfer what? It is a relationship between current and voltage. So, forward transfer resistance, right, because II is the input current, let us see, and this II is going to flow through RF totally and result in a voltage which is II times RF, with ground terminal being positive and output terminal being negative. That means, there is an inversion. So, V naught is going to be okay, II minus II times RF. Is this clear? This II will be going through this, okay, totally. Very small is current is going to flow through the transistor amplifier. Most of it will flow through RF. Why? Because I mean, Miller effect kind of thing, right? RF is going to appear as RF divided by 1 plus AV, where AV is the voltage gain of this state. That means, it is going to act like a short circuit. Okay, if AV is very high, most of the current will be pumped into RF. Okay. So, this current will flow through this and develop a voltage which is minus II into RF, and therefore, forward transfer resistance is nothing but minus RF. So, it is a current controlled, input current controlled voltage source developing a voltage which is equal to minus II times RF. So, we have desensitized by this kind of feedback the forward transfer parameter, which is nothing but trans resistance in this case, by using Y type of feedback. Now, that is known to you. What must be emphasized here is, if you now take the Y parameters of the transistor and the feedback network, everything put together, and evaluate its bandwidth. What bandwidth of what? You must remember to evaluate the bandwidth of forward transfer impedance in this case, right. So, forward transfer impedance, then that will also get what? Modified by loop gain. That means that bandwidth also is going to improve by a factor of loop gain. Everything improves by a factor of loop gain. When in a feedback network, always we can take for granted that improvement is always by loop gain. So, the bandwidth also improves by a factor of loop gain. So, this particular amplifier therefore should be used only for obtaining trans resistance type of amplifier, okay, this type of feedback, negative feedback, and it will improve the bandwidth of trans impedance. Okay. This is, we will come to that. Dual of that is nothing but trans admittance. Okay. That is nothing but Z type of feedback. Okay. So, that is going to realize an idealized version of voltage controlled current source. Right. So, in this case you must remember that it is the trans admittance which is going to have wideband effect. Right. So, you must remember what type of feedback to give to improve the bandwidth of what parameter, transfer parameter. So, if you are interested in transfer parameter as admittance, then the type of feedback to be given is in turn what? Z type of feedback, not Y type of feedback. Okay. In the case of Y type of feedback, it is only trans resistance that will have widebanding effect, not. Please be clear about that. Does it answer your question?
Trans resistance in the Y feedback case is going to be reduced by the load gain.
Correct. In the case of any feedback, please remember, in any feedback you are going towards idealization. What is idealization? If it is Y feedback, okay, it is going to become current controlled voltage source. Okay. That means the modified thing is the Z parameter. If it is Y feedback, the modified thing is Z parameter. In the Z parameter, all the other parameters will go towards 0, only the forward transfer parameter will go towards a smaller value, okay, than originally by the extent of loop gain. Going towards the 0 of the other parameters is also by the extent of loop gain. Okay. So, this is a simple way of remembering things, okay, without faltering. Okay. In terms of parameters, if you remember, you will never commit mistakes, okay, as to what gets modified and how, by what extent. Okay. That all depends upon your proper identification of the feedback, okay, and what is it that gets modified. When you give Y feedback, it is the Z matrix that gets modified automatically. Okay. All the Y parameters will simply add, and it is the Z parameter that will get modified. Okay. Those Y parameters will be divided by del Y, which will involve the loop gain. Okay. So, therefore, the Z parameters will get modified, and all the Z parameters like Z11, Z12 and Z22 will go towards 0, and Z21 will go towards the stabilized value, desensitized value. And how is it getting desensitized? Because of the loop gain coming into picture, and the desensitized value is primarily going to depend upon the feedback component. Okay. It is not going to depend upon active device. Okay.
And in that case, how is it that the frequency, I mean, how is it that we are going to get a wideband response when the impedance is going to come down?
Yeah. That this is the widebanding is going to get, see, these are Y parameters, Y11, Y12, Y21 and Y22. Okay. And the Z parameter mathematically is going to be, please tell me, this is Y, composite Y, okay, of the amplifier. The Z parameter therefore is going to be y y22 by delta y, y11 by delta y, and minus y12 by delta y, and minus y21 by delta. This is the inversion of the matrix, right. This is plain mathematics, okay. And let us take this y22 by delta y. What is delta y? y11 y12 minus y11 y22 minus y12 y21, okay. If you take this out, 1 by, okay, y11 y22, okay, 1 minus y12 y21 by y11 y22. Is this understood? Okay. So, y22. So, y22 will get cancelled with y22. 1 by y11 is the original Z parameter, right. Okay. Short circuit impedance it is, that is all. Okay. That is getting modified by a factor of 1 minus what is this? y12 y21 by y11 y22 is nothing but the by definition nothing but the loop gain. If you consider this as a voltage amplifier, it will be nothing but A by 1 plus A beta factor, that is. This A business and beta factor, these are all applicable only for voltage, whereas in this case it is a general parameter, okay. In terms of any parameter, you can say that the parameter that is getting modified by is by a factor of 1 minus P12 P21 divided by P11 plus into P22, where P is called immittance matrix, immaterial what the parameter is, okay. 1 minus loop gain is, okay, defined in terms of immittance matrix, immaterial what the parameter is, okay. This is a generalized, it is this loop gain which is going to modify all the factors, okay. If the gain is getting reduced, it will also get reduced by the same factor, that let us see. Let us now do that similarly, okay. This is done for what? This is nothing but Z11, okay. Let us do that for Z21. Similar thing can be done for other parameters, you will see it gets. What is Z21? Z21 is minus y21 divided by y11 y22, okay, into 1 minus the loop gain, okay. If the loop gain is very high, that one can be neglected. So, if the loop gain is very high, this one can be neglected, and it is nothing but minus GL. And what is it? It is nothing but into minus y12 y21 divided by y11 y22. So you will get this as plus 1 by y12. This is nothing but the total feedback factor, okay, and no frequency component comes here, because y12 is nothing but y12 of the amplifier, which is negligibly small, plus y12 of the feedback structure, which is nothing but 1 over RF, okay. Since y12 of the amplifier has gone down to very close to 0, okay, or it is very small, even at very high frequency, the bandwidth factor comes, improvement factor comes simply because of that, because of desensitization itself, okay. Is it clear or not? And if you do this similar thing here, if the loop gain is very high, you will note that it is the loop gain which makes this go towards 0, because here also these things will get cancelled with that, and it is y12 y21, okay, product which will make it go towards 0, which is not getting cancelled there. y21 is still a large factor, assuming that you are using a good amplifier with good forward transfer parameter, Okay? In all the other factors, this forward transfer parameter will be the one responsible for making it go towards 0. Okay? In order to understand more clearly, you have to work out a specific problem and see how these parameters will have the widebanding effect. What will have the widebanding effect? The forward transfer parameter will have the widebanding effect. Okay? In this particular case of our example, it is the Z parameter, okay, Z21, which is going to have the widebanding effect. Okay? So, does it answer your question? Now, these are basic things in the negative feedback that we should be aware of. Now, if that is the case, the reason we have used a single stage is because it is only in the single stage that we do not have more than 2 time constants, and single stage feedback amplifier never becomes unstable. Okay? It does not need any frequency compensation. Even if whatever be the negative feedback, okay, it is never going to become unstable because it is at most a second order system. A system becomes is likely to become unstable when it is third order or higher. Okay? That also when the loop gain is higher. Okay? So, in wideband amplifiers we select always a single stage, okay, not multiple stages. Multiple stages will result in serious problems. Okay? We will come to that. We will still go to multiple stage later. A single transistor. Cascode, okay, cascode is not a single stage. Okay, cascode is not it is a pair. A single stage cascaded to another stage. Okay, a single stage means active device may be a Darlington pair, but it is a composite device with 3 terminals. Okay, is that understood? So that kind of stage is only this for Y feedback and this for Z feedback, and therefore the other two do not exist. You please try to do this, that H and G using a single stage cannot result in negative feedback, will result always in positive feedback. So H and G feedback do not exist. Then how do I obtain other sources? Which are the other sources? Voltage controlled voltage source and current controlled current source. How do I obtain? Can you see? By simply cascading, because if I cascade a current controlled voltage source with the voltage controlled current source, there is ideal mismatch, because this is a voltage source and this is voltage control. There is ideal impedance mismatch, gross mismatch. Voltage control means it is open circuit. Okay? Voltage source means it is a source impedance of 0 magnitude, right? And therefore there is gross mismatch of impedances, and therefore it is retaining the wideband nature. Okay? So now I can cascade these two together, okay, and result in current control current source. How do I do it? I put Y feedback first, then I cascade the Z feedback. This is the ideal, near ideal what? Current controlled current source of gain equal to what? The gain also is retaining its property. How? If I apply a current here, the voltage will be input current times RF. Okay? And this is going to be directly coming here as II into RF divided by RE is the current, that is the output current. So the current gain is, let us see, if this is the input current II, okay, this current will go into this II into RF, okay, that will be divided by this, okay, that means current will be going into this stage, and it is going to be I naught equal to what? RF divided by what? Re into current is going to be in the other direction, or this is going to be minus. Actual voltage is this. So, is this clear? So, this is a wideband current amplifier of gain equal to Rf over minus Rf over Re. Now, what is the dual of this? I cascade now, in order to get a voltage controlled voltage source, I cascade with so what happens when I apply Vi here? The current in this is Vi by Re, and that current will go directly into Rf. So, output voltage will be Vi by Re into Rf. Again a wideband structure, okay, and this is what is utilized, okay, in one of the most popular wideband structures, okay, that is called this is a Fairchild wideband amplifier, which is mu A 733. Do you notice that if I have to convert this into a differential configuration for bias purposes, what should I do? If I have to convert this into if I have to convert this into a IC, okay, so that biasing is taken care of automatically without the need for bypass capacitors and coupling capacitors, then what should I do to this? I have told you the standard technique for converting this single stage structure into differential structure is to convert it into differential structure from single stage to differential, then it can become an IC. Okay. So, after break we will see how this can be converted into a differential structure for application in integrated circuits. So, we have to now see how we can convert this structure. This is a configuration which has been chosen based on our basics about negative feedback. Okay. Now, we want to convert it into an integrated circuit. This is a good exercise for us to convert this particular structure into an integrated circuit. I told you that any single stage structure can be converted into an IC by simply making it differential. Let us see. This is a single stage. As he has already pointed out, this is the output and there is a load or RC, whatever it is. So, that load exists. Okay. This may be the next stage. Okay. Right. Then I will make another structure here which is exactly identical to this. Now, I have to convert it into differential. Whenever I convert into differential, I make this into a current source. And again there is grounding of these two, that will also become a current source. So, you have the differential integrated circuit version of the so called voltage controlled voltage source. Only thing is, if you want to gain as Rf by Re, you have to take the differential output. So, it is a differential output to differential input whose voltage gain is now RF over RE. Other than that, you can now independently fix the biasing current as, let us say this is I naught 1 and this as I naught 2. Okay. These are the going to fix up the biasing currents here. And if you want to still use a wideband configuration, you can still cascade a common collector output stage. I mean, we are very liberal with the transistors now. Okay. So, instead of taking the output here, I will just put a common collector stage here and then take the output here, right. Is this clear? And then this has to be biased. So, I will put a current source here. I am very liberal with current sources now, okay, because I am designing the IC, right. So, I put I naught 3. Similarly, I do it here. And this is, if you look at it, this is nothing but that structure as it is without any modification. Let us see, identify the current sources and the respective transistors. These are obviously, what are the transistors? T1 and T2, and the current source that is I naught 2 is this, right, I naught 2. That is obtained by a reference that is getting generated. You can see this is a transistor connected as a diode. So, VEE minus V gamma divided by R12 plus R8, and you can accordingly fix the voltage here, so that you require the obtain the desired current by adjusting R7. Okay. So, this is I naught 2. Next, we have the second stage, okay, which is nothing but this structure. Here we have I naught 1, and that is nothing but this. And finally, I naught 3 is through the common collector stages, final output stages, we have I naught 3. Is this clear? Okay. So, I would be happy if you do the analysis of this circuit as a homework problem, not neglecting anything, okay, considering all the non-idealities into account. That means HIE is not infinity, or beta is not infinity, or alpha is not equal to 1, and then consider all the effects of other transistors in evaluating the gain or the loop gain, etc. Right. So, please do it as a homework problem. Anyway, simply what is the input impedance of this structure, differential input impedance? 2 RE into 1 plus HFE, straight away. Right. So, voltage control, because it is high input impedance here, because input impedance is 2 RE into 1 plus HFE. What is the output impedance? I have to be very cautious. Okay. Can you tell me what the output impedance of this structure is? Input impedance is RE into 1 plus beta. Output impedance of this, right, if this is a current source, right, you apply voltage here, V divided by RF into RF plus HIV, V divided by RF plus HIE is going to flow into the transistor, result in HFE times that current through this. Okay. So, the current is V divided by RF plus HIE plus V divided by RF plus HIE into HFE. This is the total current when I apply a voltage of what? V. Okay. This is the total current. That means V divided by this current is going to be the nothing but the output impedance or resistance, right? And what will it be? Let us see. It is nothing but 1 over 1 by RF plus HIE into 1 plus HFE, or it is nothing but RF plus HIE divided by 1 plus HFE. Is it clear or not? So, you can see that output impedance is going to be very low if the HFE of the transistor is high. So, that is why it is a voltage source. Okay. Is this clear? So, similarly for the differential structure, the output impedance depends upon RF and the HFE of the transistor. Okay. We know the input impedance, we know the output impedance, we know the voltage gain, we know all the small signal parameters of this wideband amplifier. You must also analyze the voltage swing, etc., because this is a wideband amplifier, it may be ultimately amplifying large signals, right? So, I would like you to evaluate the DC voltage at this particular point. It is very easy. Please remember, this is a wideband amplifier, that means it is a negative feedback amplifier even for DC, right? And therefore, there is DC negative feedback here. So, operating point you can evaluate only by first finding out what is the DC voltage, which can be straight away found out, and from that value you have to go back. You do not know the voltages of these 2 points. Why? There is going to be current here drawn. What will be the current? That is simply I02 by 2. So, the current drawn here is known. This voltage is VCC. But please remember, there is a considerable amount of current pumped into RF. It is not pumped into the transistor, but because there is a Y feedback as the next stage, even there is going to be considerable amount of DC current flowing in RF. So, you cannot neglect the current flowing in RF. This RF and this RF. So, you have to evaluate this current in order to find out these voltages. So, how do we then go about? Let us see here, I01 is the current. So, what will be the currents in these two? I01 by 2 and I01 by 2. So, what will be the voltage at this point? VCC minus I0. So, you know that voltage, that is fixed already. So, these two voltages will be VCC minus I02 by 2 into RC2. That minus V gamma will be the voltages at these 2 points. So, output voltages are already known. So, you know these 2 voltages, DC voltages. You know these 2 currents, you know this voltage. Now, you write down the Kirchhoff's node equation at that particular node and evaluate the voltages at these 2 points. One equation, one unknown. So, I would like you to do this problem in the hostel and come out with the answer. Obviously, it will depend upon how much current is getting drawn from here. So, please do this, and then you will know how much these amplifiers can handle as output signal, depending upon the bias voltage here. Their capability for handling signal is going to be determined. So, I would like you to come out with the voltage swing capability of the stage. That is, how much input swing it can handle, how much output swing it can handle as far as this wideband amplifier is concerned. Please determine that after determining the operating point of all the transistors. I had given this structure for some test or something like that. Then I asked what is the quiescent power dissipated in the IC. How do you do it? Yeah, please do it that way. It is VCC plus VEE into current drawn. Okay. Now, there have been cases where people have evaluated the power dissipated in each one of these devices and then added. Okay. So, it is not a joke that people have done this kind of stuff. Okay. But you can evaluate the quiescent power dissipated simply by finding out the current drawn from the supplies. Okay. Unless there is a load resistance that is connected to ground, okay, you can easily determine it by simply finding out the current drawn from VCC and VEE. Okay. So, we have now seen one such IC wherein we had cascaded a voltage controlled current source with current controlled voltage source. If you are desirous of obtaining current controlled current sources of the same gain, you have to just simply change the thing and cascade it, convert it into an IC in a similar fashion. So, now you are aware of how an IC design is conceived of, okay, starting from a single stage structure up to the final IC, okay, without bothering about biasing. Okay. Biasing is becoming a trivial thing, okay, because we can use any number of current mirrors, okay, and convert the single stage into a differential stage. Okay. Now, in the next class, we will see why not go for two stages. You just said single stage is the most preferred stage because what? The order of the system is going to be 2. If I go for 2 stages, the order is definitely going to be 3, and it is likely to cause serious problems of oscillation when using. This is what happens, right? Even in IC amplifiers, we have 2 stage amplifiers, but they will require external frequency compensation in order to maintain them, okay, stable. Okay. Frequency stability is what we are talking of, and we will see such structures in the next class. When we use 2 stages, we will automatically see that Y and Z will be positive feedback structures, okay, and H and G will be negative feedback structures. When you use 3 stages, again Y and Z will become negative feedback stages and H and G will become positive. Actually speaking, people have gone only up to 3 stages as negative feedback wideband amplifiers, but those amplifiers are not at all popular. The ones which are most popular are these single stage structures, and sometimes if you can afford to understand the working of a negative feedback amplifier, you are advised to use the 2 stage structure. Otherwise, you can simply languish in the luxury of using these low loop gain. These are all having low loop gain. Okay. If you use 2 stages, loop gain is going to be boosted up, okay, and therefore, it is going to be more desensitized, but the price you are paying is in terms of trouble due to oscillations. Thank you.